Hi, my name is Kamil Borzym. I am an iOS developer at Allegro here in Poland. And for people coming from abroad, Allegro is the largest e-commerce company in Poland and sixth largest e-commerce company in Europe. And you probably shop on Amazon and eBay, but in Poland we shop on Allegro. So today I will show you some hacks. In the first part of my presentation, I will speak about Mach-O file format. Mach-O file is a container for executables and libraries on Apple platforms. In the second part, I will speak about obfuscation. And now it may seem that those two subjects have really nothing in common, but I will show you how they correlate later. Mach-O is pronounced similarly to the main power source from Final Fantasy VII. But aside from the name, they have nothing in common. Mach-O, however, has a lot in common with Matrix the movie. This may seem to be totally random byte stream. Neo, however, can clearly see people, cars, buildings. I got good news for you, because now I'm going to give you an ultra-fast crash course of understanding the Matrix code. Apple ecosystem is going to be our Matrix. Let's freeze the image and zoom in. A lot of binary data formats start with some arbitrary value, the magic number. I think some of you can already see that the first 4 bytes of this presentation, of this byte stream, are very similar to the title of this presentation. Similar, but also written in reverse order. Why in reverse order? Because of little endian notation. In little endian notation, when you write bytes of a number, the least significant byte is written as a first one. So the number in the first 4 bytes of this byte stream is really FEEDFACE. But how can Neo even know what does this number even mean? It is simple. Value is defined and described in system headers. And Neo, he just knows all the system headers. The system header that describes Mach-O file provides definition of 2 magic numbers. First one is, it's the same as the title of this presentation. It's a magic number of 32-bit Mach-O file. The second looks just like the magic number of this byte stream, and it is a magic number of 64-bit Mach-O. Reading comments from that Mach-O system header reveals that each Mach-O file starts with a Mach-O header. So this header can be described with following struct. First 4 bytes for magic number, as you already seen. Then comes the CPU type, CPU subtype, then file type, number of so-called load commands, which we are going to talk later, and size taken by those load commands, some flags, some reserved area. Let's color up matching byte ranges in that stream. Now we can see the header on top, but those numbers, they still look mysterious. So luckily, macOS system header provides definition and description for all the values you can see here. So let's just replace those numbers with human-readable text. And now let's try to read it. So this stream is a 64-bit Mach-O. It was compiled for all subtypes of 64-bit Intel CPUs. It is an executable, and it contains 20 load commands. So reading the Mach-O system header reveals that load commands come just right after the header. So load commands are there after the header. And the base structure of a load command is described with following struct. Each load command starts with command type and command size. So let's try to color up matching byte ranges again. And we can see two load commands here. First one has a command type equal to hex 19, and it has size equal to hex 48. The white area is the payload of this load command. So if you count these red bytes, orange bytes, and white payload, you should get hex 48 bytes in sum. Then you should try parse second load command, and another one, until you get all 20 load commands. So how to understand what's inside this payload? When you should try to look for matching command type definition and read its description. I will show you some examples of load commands. For example, load command segment, which happen to be this load command, as you see, and this one. Load command segment is used to map some file region into a memory region. Load command UUID, it does not map any memory. It holds a Mach-O file identifier, the same identifier that is used, for example, by Crashlytics, when Crashlytics desembolicates your crash logs. So it will try to look desem file with matching UUID. Load command rpath holds a path to the directory which holds dependent dynamic libraries. In case of iOS app, the frameworks directory. Another load command, dyld info, it's heavily used by dynamic loader during the app startup, and we are going to talk about this load command in a few minutes. Okay, we won't parse manually the whole Mach-O file because it is really boring process. But I just replace all non-zero bytes here in the payload using ASCII codes just to show you that there are some more meaningful contents inside. But let's skip all that manual parsing. I already did the job for you. And here you can see a snippet of the load commands list. And let's take a look at few of those load commands. Load command segment, it maps first one hex 1000 bytes into some memory area. Each segment consists of several sections. And this section text, it points to a byte range. Byte range that contains all assembly of all the method and all the functions within the Mach-O file. Another load command, main, it holds just a single pointer, and this pointer happens to be located exactly in the text section. So this is a pointer to the main function. When you start your app, dynamic loader will read location of the main function and will just redirect the execution to that location. Load command load dynamic lib is used to load dependent dynamic libraries. So here you can see Objective-C runtime and Swift runtime below. We won't parse this Mach-O file manually. I only wanted you to get the general idea that it's really simple process, only boring. And you can parse Mach-O file using OTool with L parameter, and using the verbose mode will even replace all those magic numbers with human readable texts. Let's get back to this load command list, and I want to take a closer look at one section systring. As you can guess, C-string section contains all constant strings defined within the app. So load commands are just like a table of contents, and when you, if you want to take a look at the contents, you need to go to the byte range described in load command. So let's jump into this byte area. And it's pretty short that because that byte stream is just a simple sample app made just for the sake of this presentation. Let's replace all those bytes using ASCII codes. And that is how Neo saw the woman in red. Jumping between byte ranges can be really painful, but hopefully you can use OTool with S-parameter to display contents of any section in any segment. So let's display contents of Objective-C metname section in macOS system calculator. So as you can probably guess, this section holds all method names. Let's replace bytes using ASCII codes. Init with frame set transparent appearance named. So yeah, this is a nil separated selectors list. Let's take a look at different section in Mach-O file. Objective-C class name section. Again, let's replace bytes using ASCII codes. Bit field box calc button cell calc digit cell. So yeah, those are class names within the macOS system calculator. And nil separated strings list is not very complicated data structure. Mach-O contains a lot of other complex data structure. For example, there is a section which describes class hierarchy, or section which describes class properties, methods. We won't talk about them today. Instead, we'll talk about another complicated data structure. Load command dyld info load command holds a pointer to an export trie. So this may look like a tree, but it's not a real tree, it's a trie. So what's the difference? When you have tree, each node would contain a complete key. And trie is a data structure which makes searching for very long keys extremely fast, because each node contains only a key fragment. And what is an export trie? Export trie describes all the public symbols of the library. So in case of, for example, Objective-C runtime, it gives Objective-C message sent to be used by your application. So dynamic loader needs to look for the address of Objective-C message sent implementation. It will traverse from the root _ Objective-C message sent, and that is the pointer of Objective-C message sent function, assembly of this function. So this can be flat printed as this list, and yeah, load command dyld info provides the export trie, but it also provides a way to declare this other side, the import side. So here you can see a snippet of bindings lists, and each binding describes symbol used by Mach-O file, referenced by its name and library. So here you can obviously read more about the trie structure. And as you can imagine, I'll only show you a very tip of an iceberg. But good news is that there is a single system header which describes almost all important information about this topic. So every macOS contains a complete documentation of Mach-O file format. It's detailed, but also very easy to read. It contains struct definitions and human-friendly comments. And congratulations, you have all completed an ultra-fast crash course of understanding the matrix code. I'm sure all of you should now see woman in red in that stream. Anyone? Anyone? Okay. That completes the first part of my presentation. Mach-O format is Apple-specific, but all the concepts described are very similar for other platforms, that is, Android, Linux, Windows. Let's talk about obfuscation. Obfuscation is a process of making things hard for static analysis. And here is an example of obfuscated function. Can anyone tell what does this function do? Okay, you wasn't supposed to answer. Now I will show an obfuscated version of this function. And now can anyone tell what does this function do? Someone said factorial. Okay, so yeah, so it's much easier than this version. It's a control flow obfuscation. It's pretty hard to achieve because compilers usually optimize the code. So both versions could end up as exactly the same assembly. This type of obfuscation is usually used by malware. There is another type of obfuscation. The control flow here is pretty obvious, but all the symbols are unreadable. This obfuscation is a symbols obfuscation, and it's easy to achieve in case of object-oriented programming, and it gives relatively big benefits. Without this obfuscation, this function would be very easy to find, very easy to understand, and the whole app would be just very easy to crack. There is also another type of obfuscation. It's an obfuscation so advanced that it is indistinguishable from magic. And if you want to learn more about this obfuscation, I encourage you to watch the video about reverse engineering Hopper Disassembler. I will just give you a short sneak peek about this video. When you try to decompile Hopper, but not using Hopper, because you can't decompile Hopper using Hopper, it protects against self-decompiling. Well, if you see the text section, it turns out that the assembly doesn't make any sense. And it looks like Hopper Mach-O contains one additional load command that have 20 megabytes of some random data, but when it XORs that data into a text section, then it creates a true Hopper assembly. So yeah, for me it feels like magic. I spoke about Mach-O and about obfuscation because I wanted to tell you about an open source project. The idea behind this project is not to obfuscate source code, but to obfuscate a compiled Mach-O file instead. And here is an URL to MachObfuscator. It was written in Swift. And now I would like to publicly thank to two awesome contributors, Kamil Kosowski and Krzysztof Jamros. Guys, if you watch me, if you hear me, you added a lot of magic to this project. You are true Mach-O wizards. Thanks. And now about MachObfuscator. How does it work? Well, it changes contents of some sections in Mach-O file. Obfuscating symbols in Objective-C class name and Objective-C met name protects against tools as class dump or Hopper Disassembler. Swift also adds some sections for Swift metadata, and this section used to be used by mirror struct, and for the time it looked like filling those sections with zeros is totally fine. Mirror struct will still work. it will just return much simpler data. But with the latest version of Swift, it looks like MachObfuscator can no longer fill those sections with zeros. So now, by default, it will not obfuscate those sections. But at the end of the presentation, I will show you one little trick that that handles those sections. So there's also a DYLD info with the export try I showed you. And I don't really know any reverse engineering tool that uses that information. DYLD uses it during the app startup, but this can be obfuscated, so why not? SymTab, it is just used by LLDB for symbols autocompletion and by Hopper, and it can be just filled with zeros, so why not? MachObfuscator also handles NIPs and storyboards. And how does the obfuscation proceed? Well, after running MachObfuscator, it will look for all executables within the app bundle. Then it will search for all the dependencies of those executables and dependencies of the dependencies until it finds the whole dependency tree. Next, it will mark those files as obfuscable, because those files are, for example, in the app bundle, and unobfuscable because you really can't modify system libraries. Then it will get all the symbols from those files, and now it needs to drop all unobfuscated symbols. And imagine having init method in your app and init method in a system library. Now MachObfuscator cannot obfuscate init because obfuscating would break the Objective-C runtime. So those are the methods left that can be obfuscated, but if you take a look, those are the methods that describe the business logic, and the business logic is the thing that we want to obfuscate. Now, some little comparison of binary obfuscator and source code obfuscator. And yeah, there is no silver bullet. I only wanted you to show the differences. And regarding binary obfuscator, it's pretty much language agnostic. It will work regardless Apple providing any new programming language next WWDC. And as for source code obfuscator, it will probably need to be rewritten from scratch or something. And I don't know any obfuscator which obfuscates both Objective-C and Swift in the same app for source code obfuscator, and here it is not really an issue. Also, binary obfuscator obfuscates external libraries. For example, Google Analytics precompiled binary or some payment provider library. Then binary obfuscation doesn't affect symbolication because DESM files are generated before the obfuscation. And yeah, and the crash logs are just readable. In case of source code obfuscator, you probably need some kind of tool to translate your crash logs. But binary obfuscator also has some downsides. For example, it will not obfuscate any new unknown sections within the file. It probably will need to be updated, and it's not an issue with source code obfuscator. And also, some people feel really unsafe using this kind of obfuscation because they tell that this uses some kind of binary black magic. So I wanted to tell you about one additional feature of MachObfuscator. Before that, interesting fact. We had a problem with Allegro iOS app review. Well, this big company from US rejected our update, and they wrote that our app includes hidden or undocumented features. And later, during the conversation, then they asked us to remove any code obfuscation. How did this story end? I cannot tell you, but you can probably guess. But MachObfuscator has an algorithm which could protect against detecting obfuscation. It contains a list of 10,000 most popular English words, and it uses them to generate symbol names. So this may seem to be totally valid selectors list, but if you try to read all of them, then poem.doc doesn't make any sense in case of banking up. And that completes the second part of my presentation. But wait, there's one more thing I forgot to tell you about. Yeah, not by me, by Apple. They also forget to tell everyone about that. They added a new Swift compiler setting. If you set reflection metadata level to none, you could do this right now for release build, it will greatly reduce the amount of metadata within the Mach-O file. And this setting can also save a couple of megabytes from your app size. So yeah, I encourage you to read the docs with the description, but yeah, I encourage you to check this out. And let's wrap up. Here is a MachObfuscator link. I encourage you to see the README and maybe clicking this star button on top. And yeah, that is everything. Thanks for your attention. In case you had any questions, we have a lot of time to ask them now, or you can always chat with me later. So thanks.